This is geotrig lesson 2, day 2. Yesterday we talked about area of things. Today we're going to talk about volumes. So volumes are just an extension of areas, and we'll find that out soon enough. But volume works in what dimensions? Third, 3 dimensions, right? So it's the third dimensions, aka it's 3D. The room, all of us in it, is in a 3D space. The board itself, though, or your desktop, that is 2-dimensional. So your desktop, we could paint it. It has a surface area, an area. But what happens as soon as I take that surface and say I'm painting it, every layer of paint is adding actually a 3D or a third dimension to it. If you ever taken paint off of something and it's been painted several times, there's a layer, and those layers are kind of like layers of volume, because you're taking the area and you keep on applying more and more to it, going up or off of the object. It wants us to know examples of volume. So, again, I kind of borrowed these, so can we give some volume, examples of volume?
Inside of a sphere.
Inside of a sphere, or just inside of a shape, a 3-dimensional shape. Or a circle would be area, right? Because that's a 2-dimensional shape. A sphere is like a ball.
How much stuff is in a can?
How much stuff's in a can? So,
how much stuff is in a bottle?
In a bottle.
Volkswagen.
Okay, or inside the Volkswagen. Like how many people, right? You can fit inside a Beetle. Okay, I think the record is what, 20-something? Okay, yeah. Volume. So, liquid. Is there an I in there? Is that liquid?
Yes.
Okay, so liquid. Inside something, right? I think that's one of the inside something. We'll put something. An object or something. I think that might be one of the easiest ways to visualize volume. Your can of soda or your water bottle that's sitting on your desk. You could see that if everybody in here had the same exact size water bottle, we could line them up next to each other and say, this person has more volume of liquid than the next person because they drink less of it, right? It'd be very easy to line them up by the height of the water inside those bottles. Guys, how do we calculate volume of the shapes below? The first two, these two are probably pretty easy to do. What's the volume of those? Length times width times height. That's a rectangular solid. Guess what a cube is?
Same thing.
It's the same thing. It's a rectangular solid. It's not a rectangle. It's just a square solid. Right? Instead of rectangle. So again, this one is length times width times height. That's actually fairly straightforward. What's a cylinder? Pi times something, yeah.
Radius.
And a radius. Squared, yes.
Height.
So, and a height. How about pi? Yeah.
Yeah.
Radius.
Yeah.
Squared.
Yeah.
Times height.
Yeah.
Does that kind of make sense? Now I'm gonna move to the next slide because I think there's some more objects here, and then I'm gonna come back to these. Has everybody got those?
No.
Okay, I'm not changing the slide because I do want to talk about these 3 first. Do you guys recognize something in every single one of these? Something that we worked with just yesterday?
Area.
Area. Do you guys see length times width is area. Pi r squared is area. Guess what? Volume is this. You can simplify volume to one simplistic equation or formula. the AOB times
Hey, good old Mr. Konjac.
height. And what do you think the AOB stands for? The area of base. The area of the base. Guys, length and width. The length and the width is the area of the bottom. And talking about what I said earlier about that layers of paint, is that as you take a two-dimensional object and start to rise it out of the table, it starts to now have volume. So you take the base, area of the base, and you multiply it by a height, and therefore you have a solid. It doesn't matter if it's a circle, it's a circular base. So pi r squared is the area of the bottom, and then you can multiply it by 5 or 2 or 1.5. It now has a height, it now has a volume. Right? That's how you can use this. Volume equals the AOB times height. Area of the base times height. That's your key. Now, we talked about these three. These three are slightly different because it takes on a little bit of a different formula. The sphere. Does anybody know this one? We don't use it that often. You can draw a circle and another circle, kind of oblong there, to kind of show that three-dimensional shape on 2D space. But it actually, I do believe, it's 2/3 pi r cubed. Sorry about that. I definitely didn't think that looked right. So I am stand corrected. It is actually 4/3 pi r cubed. The reason I put 2/3 on there is there's actually problems in your book that actually show, guys, that if I make a can that basically, like, you guys buy tennis balls?
Yes.
And it comes in a cylinder?
Yes.
It comes in a can, like a Pringles can.
Smells all good. Oh,
And,
I buy tennis balls.
okay, shh, listen. There are 3 of them in the can all touching each other, right? And the top and the bottom of the lid. Think of a single can. It'd be kind of weird to buy a tennis ball in a single can. Those for the elite players. So the pro style ones, I guess they come in one can. Think of making a can that the ball fits perfectly snug in. Okay? If you know the volume of the can, the ball inside is 2/3 that volume. So that's where I came up 2/3. And you're going to show and you're going to build the formula for this. But it is 4/3 pi r cubed. A cone. The cone is actually pi r squared h. Hey, wait a minute. That's the volume of a cylinder. But guess what? It's 1/3. Because, guys, any cone or pyramid, so the pyramid is just 1/3 the AOB times height. Because a pyramid does not have to be a square pyramid. It can be a cone with a circle on the bottom, so it'd be a circular pyramid, I guess. Or it's a cone, they call it. What happens is you've got to build this solid shape. So there's this solid shape that the cone is in. And if you were to take away 2/3 of all of the extra stuff and make it to a point, you'd be left with 1/3 of it left. And the same thing applies for for a pyramid. This could be made from a single block of wood. What they do is they shave off 2/3 of the material, leaving you with 1/3 of it left. So cones and pyramids are 1/3 of the original area of the base times height. And again, pi r squared, area times height, AOB times height. Okay? Homework, guys, is page 24 of lesson 2, 24 and 25. Have a great day.